So, so Poisson-Lie groups were introduced by Drinfeld in mid-1980s to interpret Lie theoretically some integrable systems, and also to as a semi-classical version of quantum groups. And so let me just start from the definition. So the definition of a Poisson-Lie group is the most natural one you can imagine. So a Poisson-Lie group is a Lie group, which is also a Poisson manifold. So it has Poisson bracket on functions. This means that it has it's a bi-derivation, so it's a derivation in each variable, and it is also a Lie bracket. The condition is, of course, if you have two structures on the same set, you want to have some compatibility condition to have a reasonable theory, and the compatibility condition is the most natural one you can imagine. It is just the condition that the multiplication map G cross G to G is a Poisson map. So what does it mean? Well, it means it's a map that preserves Poisson bracket. So if we have two functions on G, and we take their Poisson bracket and then pull them back to G cross G, it is the same thing as pull them back first and then take Poisson bracket on G cross G. And what kind of Poisson bracket on G cross G we take? So we take just the Poisson bivector. So Poisson bracket, because it's a biderivation, can be defined by a Poisson bivector on the manifold, which is a section of the second exterior power of the tangent bundle, or so-called bivector field. And so the bivector field of G cross G is just the sum of the bivector field of the first and the second factor. So this is for real Lie groups, but we can make the same definition for complex Lie groups or algebraic groups or formal groups. In all of these categories, this notion makes sense. And for algebraic and formal groups, you of course can consider arbitrary ground field. And so what does it mean in explicit terms? So this means that if you have two regular functions f and g on your group G, where regular means whatever it means, depending on the category in which you're working, smooth, complex analytic, algebraic, or formal. So this map G cross G to G maps x comma y to x times y. So this means that if you pull back a function f, then you will get a function of two variables, which is f of the product x times y. So the equation that says that the Poisson bracket is preserved is Poisson bracket fg of x times y can be computed as a sum of two terms. So one of them is the Poisson bracket with respect to the x variable, and the other is Poisson bracket with respect to the y variable. This corresponds to the fact that the Poisson bivector on G cross G is the sum of one for the first factor and one for the second factor. In terms of Poisson bivector pi, which is, as I said, a section of the wedge 2 of the tangent bundle, the bivector field, this can be written in the following way, that if you take pi of xy, it's equal to pi of xy plus x pi of y. And what does it mean? So pi of x is an element of the fiber of wedge 2 of the tangent space at x, and multiplication by y means that we are right translating it by y, so it gets translated to the point x times y. And similarly, pi of y is a an element of the fiber of wedge 2 of the tangent space to G at Y, and we are left translating it by X. So it is easy to check that this can be, this equation here can be rewritten in terms of Poisson bivector in this way. So in particular, if we substitute X and Y both equal to the unit element E, then we get the equation that pi of E is equal to pi of E plus pi of E, which implies that pi of E is 0. So this means that the Poisson bracket vanishes at the unit of the group. So in particular, if your group is not trivial, then, for example, it cannot be symplectic. You always have a point E where the Poisson bivector vanishes. And in particular, the 1, I should say, not 0, is a symplectically, the unit is a symplectically. Now, PoissonLie groups form a category, which I will denote by PLGR. The objects in this category are PoissonLie groups, let's say real PoissonLie groups, and morphisms are Poisson homomorphisms, which means that they are homomorphisms of Lie groups which preserve Poisson bracket. And similarly, one can define the category of complex PoissonLie groups, PLG sub C. And so the first proposition is that the inversion map is actually an anti-Poisson map, which means it opposes the Poisson bracket, it changes the sign. So in other words, if I pull back two functions f and g under this map and then compute the Poisson bracket, then it is the same as do it in the other order up to sign, but the sign is minus. So there is a minus. And the proof is very easy. You just substitute y equals to x inverse into the equation 1 here. And what you get is this equation, pi of x times x inverse plus x times pi of x inverse equals to pi of e, which is 0, as we know. So then we can solve this for pi of x inverse, and we obtain that pi of x inverse is equal to minus x inverse times pi of x times x inverse. And so this is exactly the statement that the Poisson bracket is anti-invariant with respect to this map. Because if you compute the differential of how should x so this is wedge 2 of the tangent bundle, so we really have to look how the way it's transformed by I is by the differential of I, and differential of the inversion map at a point x is a composition of left translation by x inverse and right translation by x inverse, but with a minus sign. So, the differential is a linear operator from the tangent space at x to the tangent space at x inverse of g. And to go from x to x inverse, we multiply twice by x inverse, once on the left and once on the right. And then this is just the usual translation, composition of two translations, except that you have to put a minus. And so this is really a fancy way of interpreting an identity from calculus, that if you differentiate x of t to the minus 1, where x of t is some curve on your group, then it is the same as minus x of t inverse dx over dt times x of t inverse. So if you basically, if you differentiate a matrix function of one variable a of t to the minus 1, this is the form. Okay, so this is the proof that inversion is an anti-Poisson. Any questions up to this point? Okay.
Maybe I have one. Sorry.
Yes.
Maybe I have one. Would it be possible to give an example of a Lie group which we cannot make into a Poisson-Lie group?
Well, any Lie group can be made into a Poisson-Lie group by taking the Poisson
right.
vector 0.
Okay. Yes. Okay. Yes. Let's take a non-trivial one.
Yeah. No, I think if you have, there's probably no such examples, because, for example, if you have in the Lie algebra of this group, you have two commuting elements, then you already can construct a non-trivial example. Or if you have two elements which generate a two-dimensional Lie algebra, then you can also construct an example. I will explain that later. So I think maybe any Lie group contains such one of those. And so
all right, thank you.
Other questions? Right, so there are very many of these structures, and we will discuss some important examples of them later. But so let me say now that the main tool of studying Lie groups is passing to the Lie algebra, because that allows us to linearize the problem. And so this is what's wonderful about Lie theory compared to differential geometry. So in differential geometry, linear approximation tells you a lot, but it is not sufficient because you have higher order terms. So, for example, like if you have a Riemannian metric at a point, you can diagonalize it and bring it to a sum of squares, but not in the neighborhood of this point, and this is due to phenomenon of curvature. But for Lie groups, actually linear approximation determines everything. And this is the essence of the fundamental theorems of Lie theory. Namely, these theorems tell us that the category of simply connected Lie groups is equivalent to the category of finite dimensional Lie algebras by the functor of taking the Lie algebra of a group. And with this theorem in mind, let us see what kind of structure on the Lie algebra of G is induced if you have a Poisson-Lie structure on the group G. And this leads us to a notion of Lie bialgebra, which is the linearization of the notion of Poisson-Lie group. And similarly to the case of usual Lie groups, we will see that this is sufficient to capture the whole structure of Poisson-Lie group, and that reduces many questions about the Poisson-Lie groups to purely algebraic questions about Lie bialgebra. So first of all, let me talk about general Poisson manifolds. If you have a Poisson manifold X and a point E in X where the Poisson bivector vanishes, then actually you can make a linear approximation at this point. So this is relevant to what we are discussing because we know that the Lie group is such a manifold. Well, if you have a Poisson structure which is non-degenerate at a point, which means it's given by a symplectic form, then there is Darboux theorem, which tells you that you can bring this symplectic form to the sum of dxi wedge dyi to the standard form. But if Poisson bracket vanishes at a point, this is the opposite case where Poisson structure is as degenerate as possible. In fact, Weinstein showed that locally any Poisson structure is a product of these two examples. So it's important to understand the linear approximation of the second extreme case. So in this case, I claim that the tangent, the cotangent space to this manifold X at the point E has a natural structure of a Lie algebra. And here is how to see it. So you have the maximal ideal I in the algebra of smooth functions vanishing at X. Or you can consider germs of smooth functions, it doesn't matter. This ideal is closed under Poisson bracket if Poisson bivector vanishes at E, because when you have two functions f and g which lie in this ideal, well, you take their derivatives, which do not necessarily lie in this ideal, may have non-zero value at E, but then you multiply these derivatives by some structure constants of this pi, which vanish at E, and you sum, and you get a function which vanishes at E. So it again lies in this ideal I. So, so this means that I is a Lie algebra, a Lie subalgebra of smooth functions. And moreover, if you take the square of this ideal, then it's actually a Lie ideal in this Lie algebra, because Poisson bracket is a derivation in each argument. So if one of the argument is in I squared, you apply Leibniz rule to see that the result will also be in I squared. And so if so one of the argument is in I squared and the other is in I, then the result will be in I squared. So so this means that you can take the quotient I over I squared, and that will be a Lie algebra. It's a quotient of a Lie algebra by an ideal. And but this quotient is exactly cotangent space. And so this shows that cotangent space is a Lie algebra.
Excuse me, Pavel, can I ask another question? I'm sorry to interrupt you.
Yes.
So in this case, we just took any point on X.
Yes.
And then, so you denoted this point by little x, yes?
By E. Maybe I have written X somewhere, but I denoted E.
Ah, so the maximal ideal I is the set of functions that are vanishing at E, not at X.
Oh yes, thank you.
Yeah,
yes.
yeah, okay, sorry. Thank
it's
you.
a misprint, yes, at E. Thank you. Yes, so so this is a linear, so this shows that the linear approximation of X at the point E, well, it's a tangent space, so dual to G. So this is the edge coadjoint representation, G star, of this Lie algebra. It is well known that the coadjoint representation of a Lie algebra has a Poisson structure, which is the Kirillov constant bracket. That's the approximation of X. It's not true that X is locally isomorphic as a Poisson manifold to G star. It's true in some cases, for example, when G is semi-simple, then it's true at the formal level. But in general, it's not even true at the formal level, but at least it's a linear approximation. And so in particular, this applies to Poisson-Lie groups. And it shows that if you take a Poisson-Lie group G and take its Lie algebra, then not only it is a Lie algebra, but also the dual space to it is a Lie algebra, because the cotangent space at E to the Lie group is G star, and that is also a Lie algebra by the above discussion. And this means that we have a commutator map from wedge 2 of G star to G star. And we can dualize this map and realize it as a linear map from G to wedge 2 of G, which is called the Cobracket or co-commutator, because it's like bracket, but it goes the other way. And this delta satisfies the dual version of the Jacobi identity. So this bracket on G star satisfies Jacobi identity, and this means delta satisfies the dual of that identity. And the way to write it down is easy to check is the following. So we first apply delta to element X. This takes us from G to wedge 2 of G. And then we apply delta to the first component. And then we alternate, which means we sum over cyclic permutations. So alternator of a 3 tensor A cross B cross C is A cross B cross C plus B cross C cross A plus C cross A cross B. and then an alternator of delta cross identity composed with delta applied to X is 0. So that's the called co-Jacobi identity. And we define a Lie coalgebra as a vector space G with a linear map delta satisfying the co-Jacobi identity. And so we see that the Lie algebra of a Poisson-Lie group is both a Lie algebra and a Lie coalgebra. But that's not it. There is also a compatibility condition. Like I mentioned, if you have two structures in the same set, you want to have a compatibility condition, and we do have it here. So I will explain it in a second. But meanwhile, are there any questions? All right, so here is a compatibility condition. So what I claim is that delta satisfies some kind of Leibniz rule. So if you apply delta to the commutator of two elements, A and B, of the Lie algebra, G, then this is the same as take commutator of A with delta of B plus commutator of delta of A with B. And of course, when I write commutator with A, I really write A tensor 1 plus 1 tensor A. This is if you like, an element of the tensor square of the enveloping algebra of G, because delta of B lies in wedge 2G. So this commutator means that I commute A with the first component of delta and plus commutator of A with the second component of delta. And similarly here. And so let me explain the proof of this. So basically, this is obtained by differentiating the condition that the Poisson bivector is preserved by a group multiplication. So namely, it's convenient to trivialize the tangent bundle on the group by right translations. And that allows us to replace this Poisson bivector pi, which is a section of some vector bundle, by actually simply a function from G to wedge 2 of the Lie algebra. Namely, we take this little pi of x, which is big pi of x times x inverse. So big pi of x is, I repeat, an element of the fiber of the wedge 2 of the tangent bundle to G at the point x. So we can return it to the identity by right translation by x inverse. And then we will get just a function from G to wedge 2 of the tangent space at the identity, which is just the Lie algebra. So wedge 2 of little g. And then we can see what how to rewrite in terms of this little pi the property of the Poisson bivector. So we can capital pi of xy is equal to x pi of y plus pi of x times y. So we multiply that by y inverse times x inverse. And we have it here. And here there was a y. So if you like, you can add that here, y inverse x inverse, and so this y cancels, and what you get is so this is of course pi of xy, and this is x pi of y x inverse, and this is pi of x. So you obtain this equation here, which but if you left translate something by x and then right translate it back by x inverse, this is simply the adjoint action of x. And so we obtain this equation. Or more precisely, I should say adjoint x tensor square, because it acts on the wedge 2 of the tangent bundle of the Lie algebra. But I will drop that square and we'll write it just in this way. And now, how can I obtain the delta of the commutator? Well, I should subtract pi of xy minus pi of yx, because commutator in the Lie algebra measures the non-commutativity of our group. So I should compute the difference between pi of xy and pi of yx. And I should actually take x to be the exponential of t times a, and y exponential t times b, where a and b are in my Lie algebra. Because we know from the Campbell-Hausdorff formula, the beginning part of it, that e to the ta times e to the tb is equal to e to the tb times e to the ta times e to the t squared times commutator ab plus higher order terms. So let's compute this difference. And what you get from the formula here immediately is that the first discrepancy will be, so if you expand it in a Taylor series with respect to t, then the first discrepancy will be in order t squared. And it will look like t squared times the differential of pi at the origin times the commutator ab. But actually, the differential of pi at the origin is simply delta. So I said that we have a Lie algebra structure, but it's actually the differential of pi. That's clear from the definition. Because actually for any Poisson manifold with a point where Poisson bracket vanishes, this Cobracket on the tangent space is just the differential of the Poisson bivector. So we've got t squared times delta of the commutator AB as the first term of this thing. So this is if you subtract the left-hand sides of these two equations, this one and this one. But what happens if you subtract the right-hand sides? So these are the right-hand sides. So we will have, for the right-hand side, with pi of x, which is pi of ta, e to the ta, we will have pi of x minus adjoint of y times pi of x. So it's 1 minus adjoint of e to the tb times pi of e to the ta, and plus adjoint of e to the ta minus 1 times pi of e to the tb. And then we can Taylor expand each of these. So this is minus t times the adjoint b plus so on. And this is t times delta a plus so on. And this is t times adjoint a plus so on. And this is t times delta b plus so on. And so therefore we just get t squared here, t squared adjoint. So here, from here, we get t squared adjoint a acting on delta of b. So this can be written as here. And the second term will be minus adjoint b acting on delta of a. And this can be written as here. And therefore, we obtain that this expression here is equal to this expression here. And that's exactly the identity we wanted to prove, which is this. Okay, and then we say, make a definition that a Lie bialgebra is a Lie algebra G with a co-algebra structure delta, which satisfies the compatibility condition. And the compatibility condition is really the quality of this. And so Lie bialgebras also form a category, Lie bialgebras over real numbers and Lie bialgebras over complex numbers. And one can consider not necessarily finite dimensional ones. So this Lie bialgebras can be defined over any field, actually, or any ground field, because it's a purely algebraic notion. We can consider either finite dimensional ones or all Lie bialgebras. And the proposition is that the assignment sending G to Lie algebra of G, equipped with this Cobracket delta, is a functor from the category of Poisson-Lie groups over K, where K is reals or complexes, to the category of Lie bialgebras over K. And in fact, if you like, you can say that finite dimension. Okay, any questions up to this point? Okay. So now let me give you a few examples. So of course, there is a trivial example where Poisson structure is 0, and this corresponds to delta being 0. So any Lie algebra can be equipped with the Lie bialgebra structure. Now, more interesting examples are two-dimensional Poisson-Lie groups. So, and they correspond to two-dimensional Lie bialgebras. Maybe I should say Lie bialgebras, because I haven't explained yet correspondence to the other direction. Lie bialgebras. Well, let me take a non-abelian two-dimensional Lie algebra. There is a unique one, which is the Lie algebra of matrices of this form. And it has a basis X, which is this matrix, and Y, which is this matrix. And commutator of XY is Y. And so the question is, what are Lie bialgebra structures in this Lie algebra? Well, what can be the Cobracket? So Cobracket is supposed to map G into wedge 2 of G, and wedge 2 of G is a one-dimensional space, which is spanned by a single vector X wedge Y. So we get the delta of X is alpha X wedge Y, and delta of Y is beta X wedge Y. And the Koji-Kobe idea, so what are the conditions now?
Excuse me,
Well,
Pavel, what are
yes.
alpha and beta? Two
Some
constants.
constants, some
Okay,
numbers in K.
Oh, now you're going to find them in such a way that it works. Yeah, okay.
Right, and it will turn out that any alpha and beta work. So what are the conditions? It will turn out that all the axioms are actually vacuous in this case. They are automatically satisfied. But for the Koji-Kobe identity, it is obvious that it is vacuous. It's automatically satisfied simply because Koji-Kobe takes place in the wedge 3 of G, but G is two-dimensional, so wedge 3 is 0. But the compatibility condition can also be checked to be vacuous. This is less obvious, but also true and easy to check by calculation. And so we get a two-parameter family of Lie bialgebras, B alpha beta, but there are some symmetries. So actually, this Lie algebra has automorphisms, which are inner automorphisms, a joint action of the corresponding Lie group, and these symmetries look like this. If you twist the Cobracket by such a symmetry, you get an isomorphic Lie bialgebra. So the isomorphisms you get this way is that you can make this alpha to be 0 as long as beta is not 0. And also, if beta is 0, then you can rescale alpha and make it 1. And of course, there is B00, which is just the previous example of 0 Lie bialgebra structure. And then the example, more interesting example, which is important, which is really the kind of prototypical example, I would say, the simplest prototypical example. So this is Lie algebra SL2. So that has a basis H, E, and F, standard basis, with commutation relations as usual. HE is 2E, HF is 2F minus 2F, and EF is H. And then you can define the Cobracket by the following formulas. So delta of E is 1/2 of E wedge H, delta F is 1/2 of F wedge H, and delta of H equals 0. So this is called the standard Lie bialgebra structure. So you can check that this satisfies the conditions. And then well, you can also rescale this. So you can replace 1/2 by any scalar beta. And this actually gives a non-isomorphic one. So you will get a one parameter family of non-equivalent Lie bialgebra structures this way. So this has two-dimensional sub-bialgebras generated by HE and HF. And those are isomorphic to B0 plus minus 2 beta. So the first one will be minus 2 beta and the other is plus 2 beta. So this is these Lie bialgebras are semi-classical limits of quantum SL2, and so that's why this is a kind of prototypical example. And another thing is that the notion of Lie bialgebra is self-dual. So we have the following proposition. So if you have a Lie bialgebra G, which is finite dimensional, then the dual space to G is also a Lie bialgebra. Well, we know that Lie bialgebra means that it's a Lie algebra and the Lie coalgebra with compatibility condition. And of course, if you dualize, then the dual of the Lie cobracket of G becomes a Lie bracket on G star, and the dual of the Lie bracket of G becomes a Lie cobracket on G star. So that's clear. And the only thing we have to check is that compatibility condition goes to itself under this transformation. And that can be checked algebraically. That's not very hard, but actually it's nice to do it by using pictures. So for the pictures, you denote the bracket by this symbol. So a pair of horns looking to the left. And this delta is by this symbol. So the idea is that we have inputs at the ends of the horns and the output here. So bracket has 2 inputs and 1 output, and cobracket has 1 input and 2 outputs. And then what corresponds to the expression delta of the commutator AB? Well, we have 2 inputs A and B, and first you take their bracket. So this is the first part of this picture. And then we take the cobracket of what you get, which is the second part. So it corresponds to this picture here. On the other hand, what are the pictures for here, for the right-hand side of this compatibility condition? Well, there are 4 terms here. So the first term is A cross 1 bracket with delta of B. So what does it mean? Well, this means that you start with B, and you first compute the cobracket of B, but then you take the first component of this cobracket and take its commutator with A. And that's this picture. And similarly, 1 tensor A with delta of B. This means that you first take the cobracket of B and then commute A with the second component. And similarly, delta of A with B cross 1 plus 1 cross B look like this picture and this picture. And then what you notice is that, so what this duality, what it does, it mirror, it reflects everything with respect to this vertical mirror. And what you see is that the first and the fourth pictures get exchanged under this transformation, while the second and third picture go to themselves. Of course, this over and under crossing doesn't matter here, so we don't have to pay attention to that. And so that proves that this identity is self-dual, and so the dual of a Lie bialgebra is a Lie bialgebra if it's finite dimensional. And so the category of finite dimensional Lie bialgebras is anti-equivalent to itself by this duality, because duality reverses homomorphism. So any questions up to this point? I have a question. So how when am I supposed to stop? Anna, when am I supposed to stop?
Maybe I can answer this. I see in the timetable that it finishes in 20 minutes.
Yes. Oh, it's a full hour. Full hour. Okay.
Yes, sorry, it takes a bit of time for the microphone to turn on. Yes, so we have you going until the full hour. So this is about, by our clock, 17 minutes more.
Okay. So now I want to talk about the main theorems, main theorem of Poisson-Lie theory. So like I mentioned already, there is this great theorem of Sophus-Lie, which I formulate in modern language. Of course, Sophus-Lie did not have a notion of categories, but now the theorem is formulated in the following way. So the functor attaching a Lie algebra to a Lie group is an equivalence between the category of simply connected Lie groups, or real or complex Lie groups, and the category of finite dimensional Lie algebras over the same fields. So this theorem is also valid for formal groups, and there it is not as difficult. But for real and complex Lie groups, this theorem is more difficult because you have to prove, the most difficult part is to prove that any Lie algebra, any finite dimensional Lie algebra, serves as a Lie algebra of some simply connected Lie group. And that requires some, there are many ways to do it, and okay, it's not very difficult, but it's a non-trivial theorem. And so Drinfeld proved an analog of this theorem for Poisson-Lie groups, which says that the assignment from G to Lie G with the Cobracket delta that we described is an equivalence of categories between Poisson-Lie groups over K and finite dimensional Lie bialgebra over K. So again, it's also true for formal groups and characteristic 0, but it's not true for algebraic groups. Already, Lie theorem is not true for algebraic groups because not all Lie algebras are Lie algebras of algebraic groups. And in fact, even if you have a Lie algebra of an algebraic group, then not any delta gives rise to an algebraic Poisson structure. Now, so how is this theorem? So the remainder of the lecture, I will explain the proof of this theorem. So it says in chat, microphone is turned off. So what does it mean? Can everybody?
Before you
I think it's okay.
Oh, sorry.
Oh, okay.
Yes, I think now everything is okay.
All right. So now let me talk about the proof of this theorem. So so we need to show that this. So to show that some functor is an equivalence of categories, we need to show that it is essentially surjective and fully faithful. So fully faithful means that it defines an isomorphism on morphisms. And this actually is easy. It's an easy exercise. Hom as Poisson-Lie groups from G1 to G2 is isomorphic to Hom for Lie bialgebras as Lie bialgebras from little g1 to little g2. So why this is an exercise? So basically, there is such isomorphism in the fundamental theorem of Lie theory, and then we check that the condition that this isomorphism preserves Lie bialgebra structure is the same as it preserving the Poisson-Lie group structure. So that's not difficult to do. So the non-trivial part of this theorem is similarly to Lie groups, is that the functor is essentially surjective, which is that every Lie bialgebra, which is finite dimensional, gives rise to a Poisson-Lie group, comes from a Poisson-Lie group. But part of the work already was done by Sophus-Lie, who showed that at least there is a Lie group corresponding to the corresponding Lie algebra, which is simply connected. I should say simply connected here, of course. I forgot to mention simply connected. Similarly to the theorem of Lie. So,
Pavel,
yes.
Can we interrupt you for a second? I think there's a question in the chat.
Yes. Oh, definitely, nothing is true in positive characteristic. Even the usual correspondence between Lie algebras and Lie groups doesn't work in positive characteristics. So not any Lie algebra in characteristic P corresponds to a Lie group. And in fact, even the functor from Lie group to Lie algebra is not fully faithful. So there are homomorphisms of Lie algebras which do not lift to Lie groups and so on. So in characteristic P, things are very complicated and not at all as simple. But what I said that for algebraic groups, even in characteristic 0, this doesn't quite work because things can be transcendental and not algebraic. Now, so we need to show that every Lie bialgebra comes from a Poisson-Lie group, and part of the job has been done by Lie already. Some of the heavy lifting, in fact, that every Lie algebra, which is finite dimensional, comes from a Lie group. So all we have to do is to show that if we have a Poisson, if you have a Lie bialgebra structure on this Lie algebra, then we can actually construct a Poisson-Lie structure on the corresponding Lie group, whose underlying Lie bialgebra structure, differential of pi, is going to be the original Cobracket delta. So given Cobracket delta on a Lie algebra of a group G, we need to lift it to the group G, which means define some bivector or function pi, whose differential is delta, and which gives rise to a Poisson-Lie structure on our. And so the idea of proving this is to give a cohomological interpretation of the axiom the delta is a Cobracket. The delta is of the compatibility condition between delta and the comment. So for this purpose, I need to recall the notion of first cohomology of a group with coefficients in a module. So if you have a group G and V is a G module, so G doesn't have to be a Lie group, although it can be. It could be an abstract group, for example. So let's consider for a moment the case when G is just an abstract group. So then H1 of G with coefficients in V is just the X group in the category of G modules between one-dimensional representation and V. And what it does, it classifies short exact sequences, 0 to V to W to K to 0. Which are not necessarily split. So this means that W does not have to be isomorphic to V plus K as a representation. It does, however, have to be isomorphic to V plus K as a vector space. So there should be an isomorphism such that V goes to this subspace V here by the identity map. And when we quotient out, you get the identity map between this K and this K. And then if W is a representation of G, well, as I said, this is not necessarily an isomorphism of representations. So this means that G doesn't have to preserve this decomposition. it only has to preserve V, and this means that the matrix is going to be upper triangular, not necessarily diagonal. So there will be a 0 on this side, but not on this side. And on this side, we will have something interesting, which is going to be denoted by pi of g. And this is a function from g to v. And the condition that this is a representation is just that rho w of xy is rho w of x times rho w of y. And if you write it down in terms of these 2 by 2 matrices, what you get is the condition on pi. And the condition on pi is that pi of x times y is pi of x plus x times pi of y. Well, more precisely, I should write rho w of x times pi of y, but I will drop that and just write x times pi of y. And definition of function pi such that this equation holds is called a one cocycle of g with coefficients in v. So the space of such cocycles is denoted by z1 of gv. And there is a trivial example of cocycles, which is one coboundaries. So if you have a vector in v, you can construct a one cocycle pi of x simply by writing v minus xv. So then if you compute pi of xy, you get v minus xyv. And this, of course, equals to v minus xv plus x times v minus yv. And that's exactly pi of x plus x times pi of y. And so the space of these one coboundaries is denoted by b1 of gv. It sits inside cocycles. And then we form the quotient. And that's the definition of the first cohomology of g with coefficients in v. It's the explicit definition. And so the reason for this definition is that two one cocycles define the same extension or short exact sequence up to isomorphism, where we consider isomorphism of short exact sequences, which is a more rigid notion than isomorphism of representations V. W. So we not only want isomorphism of representations W, but we also want it to preserve this structure. So it should act by identity on V and act by identity on the quotient K. And so then you can show that two cocycles give the same extension, let's say pi 1 and pi 2, if and only if their difference is a coboundary. So H1 classifies exactly the extensions up to this kind of isomorphism. And well, I described that for abstract groups G, but you can just do the same thing for topological groups if V is a continuous representation, or for Lie groups if it is a smooth representation, or for complex Lie groups if it's a holomorphic representation. And in this case, we just say the same words, but we have to require that cocycles are in the corresponding regularity. And so then the corresponding group H1 classifies extensions in the relevant category. And there is a similar story for Lie algebras, which is purely algebraic. So you define the cocycles. So you can run the same story and you will find that the definition of a cocycle should be the following. It's a linear map from the Lie algebra to the representation, which satisfies this condition. Delta of the commutator AB is equal to A times delta of B minus B times delta of B. And then there is a subspace of coboundaries, which are all deltas as above, such that delta of A equals to A times V for all vectors, for some vector V and V. So coboundary of V is delta given by this form. And then there is an H1, which is a quotient of Z1 by V. And so we see that compatibility condition for Lie bialgebras is just the condition that delta is a one cocycle. And actually here we're going to care about one cocycles as opposed to cohomology. So even coboundaries will not be, for homological algebraics, coboundaries are as good as 0, but for us, we will see that sometimes coboundaries coboundaries will still define non-trivial Poisson structures, so they're more interesting than zero. So we will care about actual co-cycles and not just cohomology classes. And and similarly, the condition that Poisson-Lie structure, that pi defines a Poisson-Lie structure is, I recall, pi of xy equals to pi of x plus adjoint of x times pi of y, or adjoint of x squared, if you like. So this says exactly the same thing, but for groups, that pi is a one cocycle. So our job is to show that a one cocycle for Lie algebras can be lifted or integrated to a one cocycle for Lie groups. And so this is an integration problem, and any integration problem of this sort is really about solving some differential equations. But it turns out that, and you can solve them directly. This is done in my book with Schiffman, for example. But actually, in this case, the equations have already been solved for us by Sophus-Lie again. And that's because we can interpret this problem as a problem of lifting homomorphism. So we can interpret one cocycle as certain kinds of homomorphisms of groups. And then the problem of lifting one cocycles from Lie algebra to Lie group turns into the problem of lifting of homomorphisms. And that problem is a part of the fundamental theorem of Lie theory, so it has been already solved. And so for this, we will use the notion of semi-direct product of Lie groups. So this is a purely algebraic notion. Actually, Lie structure goes along for the right. It's just a group theoretic notion. So we have a group G and a representation V. And then we form the semi-direct product, which is, as a set or manifold, just a product G cross V, or V cross G rather. But the product is twisted. So the product V1 G1 times V2 G2, well, if it was a direct product, well, V is just a vector space. It would be V1 plus V2 G1 G2. But this is a semi-direct product, which means that when we carry G1 past V2 here, we have to act. So it's going to be V1 plus G1 times V2 G1 G2. So that G1 is the difference between semi-direct product and direct. And there is a similar story for Lie algebra. And you can glean the definition from computing the Lie algebra of this Lie group. So again, as a vector space, it's going to be V plus G, but the bracket is going to be twisted. V1 A1 bracket with V2 A2 is A1 V2 minus A2 V1 and comma A1 A2. And then here is a proposition which interprets cocycles in terms of homomorphism. So the first is a group theoretical statement. Pi from G to V is a one cocycle if and only if the map G goes to pi of G comma G is a group homomorphism from G to semi-direct product. And the second is a similar statement for Lie algebras. Delta from G to V is a one cocycle if and only if the map A goes to delta of A comma A is a Lie algebra homomorphism from G to VG. And I leave this as an exercise. It's completely straightforward. And so a corollary of this is that any one cocycle for Lie algebras can be lifted to the group. So it gives rise to a one cocycle pi of the Lie group, which is regular in the corresponding category. So smooth, holomorphic, formal, and so on. And its differential at E equals delta. So that's simply the second fundamental theorem of Lie theory, which says that every homomorphism of Lie algebras, so this capital G is simply connected here. So simply connected. any homomorphism of Lie algebras gives rise to a homomorphism of the corresponding simply connected groups. And so the proof of this corollary, with which I will end today, is the following. We just turn delta into a homomorphism, delta tilde, from G to V semi-direct G. And then we exponentiate this homomorphism to a map, a homomorphism from group G to G semi-direct V. And so for this, we use a second fundamental theorem of Lie theory. And then we write it as pi of G times comma G and extract the first coordinate pi of G. And that first coordinate is a one cocycle. And so in particular for Lie bialgebras, we can take V equals to wedge 2 of G. And this shows the existence of one cocycle pi from G to wedge 2 of the algebra, whose differential is delta. We are not done yet, because we also need to show that this pi defines a Poisson bracket, which means it satisfies Jacobi identity, and we will do it tomorrow. Okay, maybe I should stop here. Thank you.
Thank you very much, Pavel. Okay, so we maybe have time for one question. There's a question from the audience.
Okay.
Can you please explain the mirror argument you had
Yes.
in your pictures? Thank you.
Right. So, yeah. So I wrote so I need to show that this axiom, which is the compatibility condition between delta and the commutator, is invariant with respect to switching delta and the commutator, or rather replacing commutator with the dual of delta and the delta with the dual of the commutator. Well, so that corresponds to, so I'm going to denote everything by pictures, where bracket is denoted by this picture here, and cobracket is denoted by this picture here. And then, well, exchanging bracket and cobracket is just a reflection with respect to the vertical axis. So that's a way to write. So you can do the algebraic proof, but if you try to write down the algebraic proof, you will see that this is really about showing this symmetry. So we have to show that this identity. So if I write down my identity in pictures, I will get this thing here. And then if this duality procedure is just reflecting with respect to the vertical axis. So if I take here this picture, I will get this picture here, because this line is going to go this way. But if I reflect this one, it goes back to itself. And if I reflect this one, it goes back to itself. But since all these pictures are present, I will, when I dualize this identity, I will get the same identity, with the only difference that the fourth and the first term will switch. So that shows that this identity is invariant with respect to this duality. Okay.
Thank you.